Okay. This is all right. Welcome out there. Okay, I'm going to go ahead and get started here. I've got a new topic. It's one that we've kind of hit upon a couple of times, and that's discussing interrupts. I haven't talked about interrupts yet in this class, right? Has anybody ever heard of an interrupt with the microprocessor? You know what an interrupt is? Somebody stops you from doing what you're doing, and you have to do something else to take care of it. Well, in the microprocessor world, we have a lot of interrupts are used for a lot of control applications. For alarms go off up there. So what an interrupt does there, and I've stole some slides, as you can well guess here. I haven't done anything with them there, but I'm just going to use these, and then I'm going to go back and look at the two reference books we're using and kind of pick up some points on interrupts up there. I will say that I went through, and this is not one of these topics I didn't discuss yesterday, as you study for the final. So this is one of these topics you probably need to understand out there, because it is a huge part out there. So let me just kind of go through here and talk a little bit about interrupts right there. Okay, this is the definition. An interrupt is an external or internal event that interrupts a processor to tell it that a device needs service. Now, this definition is not probably one that I would use, because it may not be a device. It may be something internal, such as a timer. We haven't talked about timers a great deal. That's our subject for next week, to look at timers. We'll modify our previous program with Blinky to use timers in order to set our speed. That way we have a little bit more control. But it causes that there. Now, the way the example I like to use is, many years ago I worked in a hospital, back when I was going to college. I actually worked there, and they have the nurses stations, right? And nurses, every room in every hospital, at least in the U.S., has a call button, and there's also equipment in rooms that will generate alarms. If you have a heart monitor and the person's heart stops, it would be nice if the nurse has that notice that goes on. So there's usually a little console on the nurse's station that has little lights that come on that says, that the patient in room 222 wants service. That's there. So what happens typically, and again, I'm going to be a sexist person here and just simply talk about American nurses that typically are probably 85% female. I think that's probably true here too, isn't it? Most nurses are probably women. Is that true? Yep. Okay. That's there. And most American nurses like to read, especially working the night shift, in order to pass time. Out there, and they usually read trashy romance novels. Out there, and of course I get in trouble because I have an ex-wife that's a nurse that likes to read trashy romance novels. Whenever I said that, she always got mad at me. But that's the situation there. So, but regardless, what happens, when they get an alarm is they have to go through a series of events. And what we do with a microprocessor is we have something here called, and I'm going to say hint, you should know this for sure, is an interrupt service routine. If we're going to be using interrupts with our microprocessor, we have to write a special subroutine that's there. And a subroutine, of course, is a section code that we can call with a call command. Or in the case of an interrupt, we don't have a call command. The processor will do the call for us when the interrupt is generated. So, that's there. So as a result of whenever this interrupt occurs, the processor has to handle that, and we have to know what to do when that interrupt occurs. So in the case of the nurse's station, if the heart monitor says stop, they would call, again, I'm using American terminology, but you've probably watched enough TV, a code blue. A code blue means that a patient's heart is stopped and they have a protocol where they bring in the machine and the paddles and perform CPR and go through a series of events. That's the interrupt service routine. They know what to do when that particular interrupt occurs. Now, if the call button goes off, the interrupt service routine for a nurse is more likely to get up from the nurse's station and walk down the room and ask the patient what they need. And then the patient would say what the needs are. And, I'm in pain. I need more pain medication, or my pillow's not soft enough, or can you adjust my bed, or I need to go to the toilet. So, and if it's a patient that's immobile, then the nurse would have to accompany them. Again, it's a different service routine. They go through two different operations because there's two different types of interrupts. One is a piece of equipment that has gone off. Another piece of equipment may be an IV pump. An IV pump is a pump that takes the bottles that hang next to the bed that you see that contains fluid. Usually it's it may be plasma, it may be blood. Usually it's just saline solution, which is just salt water with drugs have been added to it in order to hydrate and give the patient drugs. That bag is gone empty, and that sounded an alarm. Well, the nurse would do two different activities. If the IV pump alarm goes off, she would grab a bag of saline solution or whatever she's using to give to the patient and hang a new bag, versus the heart rate monitor stopping. So we have these interrupt service routines that there, and we have to write those. Those are things that we have to write there. So as we look at our interrupts right here, now we have the option of not using interrupts with microprocessor. There's another technique called polling, and polling means that I go around what we call a merry-go-round, and we check each activity. That would be the case of, say, a security guard. If you look at the security guard here at UniKL, you see him on his little moped, right? He rides the motorcycle around the campus, checking all the various doors, checking all the various parking lots. He does these rounds So as far as I know, and don't quote me on this, and if anybody listens to this, I don't know the answer, there aren't security alarms on most of these buildings. I haven't seen signs of them So if a door opens, he doesn't get the interrupt to come check on it. So he has to physically go around and check all the doors So which one is more efficient? Personally, interrupts, I think, are probably far more efficient. But we have some overhead we have to do. None of our programs we've written and looked at this far use either, really. We've just been So by polling, you simply go around and check each one. So those are the interrupt driven. The advantage of interrupts are very simple, is that they can serve many devices at the same time. Now, one of the disadvantages of polling, which I don't know if these slides talk about, since I've plagiarized the slides. I didn't plagiarize them because I left the name of the person, but I'm using them. Well, the author put them on the web, so I guess he intends for people to use them, right? I got them from his website. So, but regardless, the advantage of interrupts is that if I'm servicing one routine and another event occurs that has higher priority, I know about it and I can go service that. The case of the security guard going around, he could be interrogating somebody in the parking lot that he doesn't think belongs here, who's probably a student that came home too late, right? They were out eating, drinking Taytaric and didn't get back till 12:30, and they're supposed to. What time's your curfew on campus? What is 11? I think, isn't it? What's that? 11. So they get back at 12:30. So the guard's busy talking to them. Well, someone's stealing a car in the back parking lot. He doesn't have that. He can't be in two places at the same time. Where the interrupt could be, the nurse is sitting there arguing with the patient in room 312 about the position of the bed. The heart monitor goes off in room 320. That alarm tells the nurse to stop working on the bed and jump over there. The heart monitor has a higher priority than the patient's call button. So we have what we can call priority that they are based on an assigned priority. And we'll see it here in a few minutes. I'll bring up the other textbook, and it has the table of the priorities, which one are more important, which is not. Another thing that we can do with interrupts that is very important is we can mask interrupts. That's there. When I say a mask, we mask an interrupt is that we basically ignore it. That's there. The patient in room 320 calls the nurse every 15 minutes to have their bed readjusted. I mean, this is a 85-year-old man who's got nothing to do with his time but to complain, right? And the nurse has got 15 other patients to take care of. She's not going to entertain this person. So she basically unscrews the bulb from her stand. That's there. So that she doesn't see the call anymore. Or she masks the interrupt. So there's certain activity interrupts we choose to ignore at that time. That's there. So it's one of those cases that and we have interrupts that are maskable and interrupts that are non-maskable interrupts. A very high priority interrupt would usually be assigned to a non-maskable interrupt where we can't ignore it. It has to be processed. That's there. So I'm just kind of going through all these here. We won't get much of an opportunity to actually write some code for these this term, although I wish we did. We will. The next lab that we'll do next week will be using the timer interrupt. So I'll be talking about the timer, and then we'll use the timer interrupt because it generates an interrupt. So we will get some practice doing an interrupt service routine. So for every interrupt, there must be an interrupt service routine or interrupt handler. So remember this term SIR, that there. And that's our interrupt service routine. Whenever an interrupt occurs, the microprocessor runs its routine, and for every interrupt, there's a fixed location memory that holds the address of that. So there's some overhead. Here in a few minutes, I'm going to be showing you a table that shows where all the interrupt service routines occur, that lists the address of where you place that. The way that we write our code, we simply we will first load into the interrupt vector table. That's another term that the interrupt vector table, the address of our service routine right there. So, and we'll see this a little bit there. So the group of memory locations set aside, these are part of the special function registers that have all the addresses of our various interrupts that we can call. There's like 15 of the various interrupts we can have. From the serial port, the timers each generate interrupts. There's some external pins that we can have. The reset pin itself is considered an interrupt, right there. So that is those are some terminology right there. So what typically happens, and this is the chain of events that occurs, and this is an important discussion of the chain of events, is that it finishes the instruction that it's executing. Right there. It saves in other words, it does not stop mid-instruction right there. So that's the nurse is reading their trashy novel. They finish the sentence that's reading. I've never seen anybody that reads a book that stops mid-sentence. That's there. They'll go ahead and finish the last 4 or 5 words. That's there. So they finish the instructions, and then it pushes onto the stack. The stack is a special place that there's push and pop commands. Push pushes the number onto the stack, pops it off. It's last in, first out. So it's just a place, I look at it as a post-it note. It puts the bookmarker in the book. So, our nurse finishes sentences, grabs a bookmarker, a piece of paper, sticks it in the book, and closes the book so she knows where to come back to when she's done servicing the interrupt right there. So the way that the processor does that, it pushes onto the stack. And again, a stack, there's commands called push and pop that push data onto the stack. It's a place we set aside memory just to store information. The stack is also used for the call command. When we do the call command, we also push the addresses onto the stack, the return address. So the stack is used there. We don't have to do anything as far as pushing and popping ourselves. The processor does this for us. So all we do is just the interrupt occurs, the instruction is executed, the return address is pushed onto the stack. In other words, it's stored. Then it saves the current status of the interrupts internally, so in other words, it just keeps stack, just stores that. Then it goes to a fixed location in memory called the vector interrupt table and looks at that location for whatever interrupt occurred and gets the address of that subroutine, the interrupt service routine. So it goes to that table, and in that table contains the address of where it needs to go to service that routine, right there. So it will actually, what it'll do is it'll take that data from the interrupt service routine and actually just move it to the program counter, right there. Right there. So once it gets the address of it jumps to it. So it does a jump. And this can be a long or short jump. It's a absolute jump. In other words, it contains the address. It starts to execute the service routine until it reaches the return from interrupt command. The return from interrupt tells the processor that it's done executing the interrupt. It's gone through the protocol that needs to be done. Upon doing that, it first gets the program counter from the stack. It pops those 2 bytes off the stack because the program's counter is a 16-bit register, because the micro 8051 that there is an 8-bit processor. It needs 2 locations for that, so it pops that and puts it into the program counter, and then it just starts executing at that address right there. It just picks up where it left off. Right there. So going back to the nurse's situation, they've taken care of the patient in whatever room they've taken care of. They've done what they've done. She walks back to her nurse's stand, picks up her book, goes to the bookmark, takes it out, and starts reading again. So it's as if nothing ever happened. That there. So this is a very, very straightforward process right there. So there are multiple interrupts. We'll look at several of the others here. Now, our processor doesn't have all the ones because we've only got 18 pins on our processor. That there. But the reset is obviously an interrupt. Oh, welcome. Glad you guys could join us here. You know, if the president of UniKL ever listens to these, they're going to say, all right, who are these students that are entering late? I want to know their names. That's there. Fortunately, there's no camera turned on, and I'm not reading off names as folks walk in, so that there. So, that there. But regardless, of course, coming late to this class doesn't necessarily hurt you that much since I put the lecture online anyway, right? That there. Okay. The highest order interrupt, of course, is the reset pin. If you hit the reset pin, no matter what the processor is doing, it goes to the reset vector. Right there. So, 2 interrupts are set aside for the timers. We actually have more timers on our processor than this particular, this discussion. These slides actually talk about the core 8051, not the Silicon Labs. It's got 4 timers or whatever. But each timer has an interrupt that occurs whenever the timer overflows. It will generate an interrupt. And that's the way that we set up our counter. We'll set up our timer for Blinky, is that we will actually start the interrupt, and every time it overflows, then it will, and we can get very accurate times by using these timers, assuming again that our clock frequency is accurate. That there. If we're using the internal clock, remember that's plus or minus 20%. I keep pointing that out. That internal clock is plus or minus 20%. So if we're using the timers to, generate time delays that need to be very accurate, then we have to use the crystals. That there. But the timers will actually have 2 interrupts. There are some pins set aside. These have to go through the crossbar if we want it on our particular chip, because we've got only 16 pins available for general purpose I/O or whatever purposes. If we want to use external interrupts, we have to set them up using the crossbar to say that we want to use external interrupts right there. So, and serial communications, if we're using the serial port, it also generates an interrupt. Serial communications is for talking to other processors, as I've mentioned before, that there. And there. So if you're doing serial communications, whenever a byte is received into the serial buffer, it generates an interrupt. Whenever you send a byte out and it's completed, it generates an interrupt. And it uses just one interrupt, depending on whether you're sending or receiving. That's there. So we will come back and talk more about serial communications before the end of the semester. That there. So this is kind of a short version of the interrupt vector table. I'll look at the more involved one right there. And as we look at here, reset is at ROM location 0000. This is all in the code memory. So when we program this 8051 and we download into its flash ROM, as you did in the lab, what it does is it puts in the address of the start of our program, right there. Usually, what loads into reset is the address of main if you're writing the C code, and the compiler will take care of that. Or you put, actually, usually you put org 0000 and then start the long jump to your program name there, right there. So, and we'll look at. I'll pull up code and we'll look at there. We also have external interrupt hardware. We have our timer 0 interrupt, another external interrupt, timer 1, and our serial com interrupts. And these are all various that they're. Oh well, yeah. See right here is what I was talking about. Right underneath there, you can see typically right here that these interrupts don't give you much room. Right there. Let me just kind of point out here. Their reset is 0000 right there. So upon reset, it's going to go there. Wake up ROM reset location, and the only thing you put there is long jump main. Right there. And then of course you would do that to any other interrupts that you want to use. You would just put an org, and then you would put, say, if you have timer 0, you would put org. There's also there's other ways of handling that. Here, but this is typically this is probably the cleanest little example here. Org is the location in the interrupt vector table for the reset button. When you hit the reset or power on reset, you want to go to your pro code, which is right here. Now in this particular case, the programmer starts the code at 30. You can start your code anywhere you want within code memory that's allowed right there. So 30 is, we're bypassing the interrupt vector table and the special function registers right there. So upon reset, all interrupts are disabled. Right there, none will be responded, with the exception of a non-maskable interrupt if we have one on our processor. Not all processors have non-maskable interrupts. But their interrupts must be enabled in software. There's an interrupt enable pin, and you can go through here, and we have a special function register right here, which will basically tell us where IE.7, it disables all interrupts. You can see, and we can enable or disable these must be set to 1. If we put a 1 in a particular bit, then we enable the interrupt. If we put a 0 there, we disable that interrupt or mask it right there. So these this is a vector table right there. This is going to go through the steps, and I think if I haven't posted these slides, I will that there. But I'm going to leave these slides here in a few minutes and go back to the to the Silicon Labs book that talks about that there. So again, EA just simply has to be a 1 if we want to enable our interrupts, and that there. And this is done in binary. You could do it in hex. It doesn't really matter. Or you can set the bits individually. But we have to. IE is of course one of those special function registers that's defined in our .h file that we include right there. And I will show an example in a few minutes that uses Blinky for a different processor right there. Then again, the timer whenever we have the timer flag is raised, whenever it rolls over in polling, we have to wait till that there. But we have a interrupt that whenever our timer our timer overflows, it will generate an interrupt. And we'll talk about timers. Matter of fact, the example that I'll be showing you uses the timer right there. Matter of fact, let me just jump here out of here. Let me go ahead and bring up the Silicon Labs. Where is my Silicon Labs IDE? I thought I had it right here. It is. I'm not. Okay. All right. This particular one. This is there. Let me close this project. Close project. Right there. Let's open a file here, and I'm just going to pick up a general one here. Right there, see Silicon Labs. Oh, we got a lot of chatting going back now. Examples, and I think the example for this one here actually use. Oh, it doesn't have it. That one doesn't. Let's find one. That's right, I had to write Blinky. I couldn't use their example here. Oh, this has got the, we don't want that one, closed file. Let's pull up another one here. Oh, they're all using the delay loop. I don't want the delay loop. We've got. I should have had this up before close file. Oh, okay. Well, I guess I don't have an example for you here. Right there. I know that I've got one. I know that there's one up. There's some of these. Try one more here. No, these are all using the delay loop. Okay. Right there. So main CSEG at 0 right there. Somewhere in my code, maybe I wrote it myself. That's why it's not there. I don't have it with me back there. But we will. I'll just go ahead and use that there. So timer 0 generates a square wave right here. Right here. Now this particular one does something that we normally wouldn't do. This is an example here. Org that there you have 3 bytes in the interrupt vector table available to you. This particular example does something I would not do. Instead of doing a long jump like we do with here to more org, it actually just does, the timer 0 simply, is the location in the interrupt vector table for timer 0. And then it toggles the bit. It just turns the bit on or off, and then it does a return. Normally, you would just put the long jump here, but because the code is so short, this particular programmer opted not to write an interrupt service routine, actually serviced it right there in the vector table. That's a bad habit to get into. But he did it. That there. This is normally the way you would handle that there. The only thing that's different about this is a normal subroutine return just uses RET for return from a subroutine. But because interrupts are handled a little bit differently, we use the RTI right there. So again, this just simply gets 8-bit data, sends it to port 1 simultaneously, while it sends a square wave at 200 microseconds on pin that there. It uses a timer 0 to assume that there. So this particular example, we would have set up timer 0 in order to overflow every 100 microseconds. And the reason I say every 100 microseconds is because we toggle that pin once every overflow. So we toggle it high, then 100 microseconds we toggle it low, and then another 100 microseconds. So that the frequency is the period of the square wave is going to be has to be toggled twice per every pass there. So that there. I'm trying to find a better example here. Okay. Main. This sets up the timer. Again, we'll talk about the timer next week a little bit there. And then this sets up our interrupt there. And notice that what we're doing here is we just simply, upon power up, right here. Okay, where did I lost it? Okay, this is the main right here, and all we're doing right here is we're doing two things at one time in this program, and we're using that there. Here is all we're doing here is this part of our program right here is just setting up the timer and enabling the interrupt. So we're moving into our timer mod, special function register, timer 0, mode 2, and again we'll look at that in more detail. We make ports 0 an import port by writing alt 1s to it, and then we move into our timer 0, the high order byte, a negative 92, in order to make it time down properly, because every clock cycle it's going to add one, and what we're looking for is how many clock cycles does it take, and we'll go into that more detail. We enable the interrupts right there, is what we're doing right there, and we start timer 0. We just simply start that there, and then this here is all we're doing is reading port 1 and putting it right back out on port 1, or reading port 0 and putting it right back out on port 1. We're not doing anything else up there. And this is an infinite loop that doesn't do anything. And so our square wave is not done at all in our code right there. We do nothing to generate our code, our square wave in our code. But then we have right here our timer, our interrupt service routine. So we go to org 1B, that's from our interrupt vector table right there. And we went back to our interrupt vector table right here. Timer 1 is 1B right there. That's where that came from, right there. Right here, right there. So, and then we do a long jump to ISR/T_T1. That there, and then here's our right there, and they don't show the time 1, the main program right there. Okay, and here's our interrupt service routine right here, right there, and ignore these comments for right there. What this simply does is we move forward into R2, we clear that. And this is our code that we write to services. Starts timer at there. Notice that we have to restart the timer here. Right there. And again, this is a similar type thing there. Let me kind of bail out of this right here, because this is getting into things that I don't want to. And let me jump to. And here we go. Right here. Now let's just kind of jump through this because deals a little bit more to our processor and how am I on time. Okay, we're in good shape on time. All right. Okay, again, this is the same type of information I talked about a few minutes ago. It kind of gives it to you in a little bit more detail. Text up there. Interrupt is an event or occurrence or a condition causes a temporary suspension of a program. Very wordy, very up there. It basically means something's happened, we need to do something. Control is then passed to the interrupt service routine. Executes that. Once it finishes, it returns control back to where out there. That's the same thing that we've talked about. Sometimes, now this is the key thing that I was talking about here. This is worded a little differently, is that sometimes multiple interrupts happen at the same time. I gave the example, the nurse is servicing the patient that their bed is not comfortable. Then as a result, the alarm goes off in a room down the hall. They need to stop adjusting the bed and go down service it. That's a higher priority interrupt. Now, our processor actually supports, this is the F20, which is very close to ours internals up there. It supports multiple interrupts up there. Now, the F20 is the same family processor, it's just a larger one. It has 4 external interrupts. Ours has, I think, 2 or 4 in my there. I think we have 4 timers. We have 1 serial port, and each interrupt has the pending flags that are located in a special function register. So whenever an interrupt occurs, we have to look at that there. So if 2 occurs while one's being serviced, there's 2 approaches. One is the polling, or the other is the 2 or that there. I'm not going to get into detail that there. So that there, this is set the enable bit, global bit, and then we can do a logical OR with setting the timers. You see, timer 4 is in the extended, because we have so many interrupts in the R8051, we actually use 2 special function registers right there. So there. So the second instruction there can be replaced by setting that bit there. And we look at that there. The priority structure, this is our priority structure. Again, it's more complicated than the one we saw in the slide a few minutes ago. Considerably more out there. But again, it's the same basic order there. We go up to here, but we've added the UART here. 23 is our serial. Timer 2, we have our SPI. There are serial peripheral interface, which is another serial interface there that didn't exist on the old 8050, the original 8050. Another late comer. All right. That's there. Boy, 9:15. That's there. Of course, now I just told on myself because now there's a reference point of when I started the class. That's there. So, because I've avoided that. Anybody watches lectures would probably assume that I started it right at 8 o'clock, right? And now by putting that, everyone will figure out that I started the recording. But I tell you what, if someone wants to sit there with a watch and time my lecture and see what time I started the class, let them. They got more time on their hands than they have work to do, right? So, okay. So as we look at this code right here, this table right here, this table is an important table because it lists the order of priority of all of our interrupts right here. Right here. That there. This table, it lists where the interrupt vector is. That there. It gives the priority in which there occurred. So if there's an external interrupt on pin interrupt 0, which is that there, it's going to be processed before a timer overflow. So if it's processing the timer overflow, it will go and entertain this one and then come back. That there. So the stack will have 2 return addresses right there. So that there. This is the flag TF0, timer overflow 0. That's there. And this is in the timer, condition, special function register bit 5. Right there is what that says. And the enable flag is an ET0 right there, or IE.1. That's it. That's our interrupt enable byte right there. Right there. Yeah, and I'm out of coffee. Or coffee from home. I know I'm not supposed to drink in this room, but I cheat too, right? That's there. But I got a spill-proof cup, so that's there. Got to have coffee in the morning. But as we see, each interrupt that we have has a location interrupt vector table, where if we're going to use that interrupt, we would enable the interrupt. And again, the interrupt, this tells what bit you would want to set that there. And the easiest way with our processor is just use the set bit command that there. And you just simply set byte setb ET0 in order to use that timer right there. Right there. And this just gives the priority control right there, which I typically don't worry much about. But this is that there. So any interrupt we use, we have to put in our code, and as we go through there, right here. This is an example of where what we have to do. We always do the CSEG at 0, and then we do our long jump for main. That's part of our code. Whatever piece of code we write, we have to have those two lines in there. Because what that does is it sets our code segment at location 0 or right there, and does a long jump to our main. And then we use the org in order to tell it the location we want to put this command, long jump the timer for interrupt right there. So we go through here. This is our normal code right here. My code right there. Segment code, it's in the code segment. Switches code bank right there. RSEG using 0 right there. Again, we put that there. This is our entry point to our code main. And then we have a bunch of code here. We would normally end our code somewhere in here, there. And then outside our main routine, we would have this function, our interrupt service routine. We would put the label there. This label has to match what's put in our long jump right here. These two have to match each other right there. Because what happens whenever timer 4 overflows, it will go to this location right here, 83. And the reason it gets 83 is that's right here, timer 4 overflow. That's location in this table. So this table tells us what to put here before the org. And normally you would just follow that with a long jump to the interrupt service routine. That's the normal way of handling interrupt routines right there. Right there. And then the rest of the code we write just as normal. This is from here to here we just write as normal. But whenever timer 4 overflows, it will go here, services routine, and go back. Now, actually, in our particular one, I think all I'm going to have you do is just increment a counter, and you're just going to stay in a loop till that counter zeroes out, and then do something right there. If this says that there, it says if the interrupt service routine is small, 8 bytes or less, there's no need to jump to a different area in memory. That's there. Now, keep in mind that you're allocated only 3 bytes in the interrupt vector table for each interrupt vector right there. Go back to this table here. You see you're allocated, well, these here you're allocated a little bit more, but 1B13. Yeah, it looks like they're giving you anywhere from 3 to 8 bytes right there, depending. I personally almost always use, I guess 8 bytes is the standard other than the reset. I've never worried about that because I've always just did the long jump. Just simply because Murphy's Law, has anybody ever heard of Murphy's Law? It's a saying in the U.S. I don't know who the heck Murphy was other than he was Irish and had a lot of bad luck. But Murphy's Law says if anything can go wrong, it will. And then there's the addendum that says at the worst possible time. So Murphy's Law, it means that if something's going to fall, it's going to give you trouble, it's going to. And if it can give you trouble, it's going to. That there. Cars are an example. When does the car break down? When you're on the way to the hospital to take your wife to deliver a baby, that's when the car doesn't start, right? That's Murphy's Law. Things will break. If something can go wrong, it will. And Murphy's Law tells me that as soon as I write an interrupt service routine that's under 8 bytes, something's going to change, and I'm going to have to modify that, and it's going to now be 10 bytes, and then I'm going to have to move it. So I may as well just go ahead and stick it somewhere else in memory to begin with. That there, because chances are, unless it's something like just increment a register, then typically we almost always have to. That there. So we have some external interrupts. We talked about those there. I'm probably going to wrap this up because the latency just simply talks about the fact that it does, that last one interrupt is asserted before it begins. It depends on the CPU with data that there. The fastest response is 5 clock cycles, system clock cycles, because remember I said that anybody that I know that reads a book will always finish the current sentence right there. The processor finishes the current instruction. So it could be 5 or 6 clocks or 4 to 5 clock cycles before it actually services the routine. Now when you're talking and these are system clock cycles, not instruction cycles. If you're talking a 2 megahertz clock, you're talking 50 microseconds per clock cycle roughly, right there. So you're talking, you can have a latency of up to 200 microseconds. For most of our control applications, that's not very long. Up there. So typically, that their maximum response time will be detect 1 clock cycle. It's 18 clocks, system clocks. These are clock cycles right there. So that's right. There's three system clocks to every clock cycle. So therefore, we're looking at it could be up to 18 clock cycles. We'll say 20 clock cycles. So you're talking you're talking maybe a couple of hundred microseconds, but definitely within a normal response time. There's very few applications that you would use an 8051 for that a delay of 500 microseconds is going to cause you a headache. I mean, that's a very short period of time, right? Even your gasoline pump that's overflowing 500 microseconds is how much gasoline that pumps out in 500 microseconds. 500 milliseconds is half a second. So you've got, 1,000th of that. So you've got, what I'm saying, 500 microseconds is half of 1,000th, so it's a pretty short period of time. I think you probably get about 4 drops would overflow out there. Very, very short out there. Okay, the interrupt service vectors, routines. These are the registers that involved right here. This is the main. This is the interrupt in IE right here, and these are the bits associated with it. Bit 7, as we talked about, is our global enable. These are all the various ones. We've got general purpose flag up there. We in the previous slide that I had there that said that was not used. We still don't really use it right there, but it's a flag you can set or not set. That they're just free if you want to flag somewhere. Up there. You've got your timer interrupt 2. Your enable the UART, enable timer 1, enable the external interrupt 1, interrupt timer 0, interrupt external 0. So out there, these are all the original 8051 interrupts. This next table is the ones that they've added to it. Because remember, the original 8051 only had 2 timers. Now we have 5 timers, so we have to have another place to put those. And so that goes into our second interrupt right there, and they call it the interrupt priority right there. And that's not the right one. I'm on the wrong slide. This is priority control. I wanted to skip the priority control. The extended interrupt, this is the one I wanted to go to right there. Out there. I wanted to skip the priority simply because out there. And this just enables the comparators and the ones that are added on right there. Because as you recall, the original 8051 only had 6 interrupts, right? Yeah, you remember. Someone's not halfway listening. Better they just woke up. Which one is that there? But regardless, the R8051's got 22 interrupts, so it needs 3 bytes to store all the enables right there. That's why we have, if you look at either of the 2 books other than this book, you'll see just this table here. These 2 tables are not in the original 8051, these special function registers right here. Right there. So, that's there. And then we also have the priorities, which I'm at there. This is our interrupt flag registers that there, and we won't get into the flag registers. That's really all I have on interrupts. I think that there a lot there. We will do a lab next week. We'll go over the lab on Monday, but we will do a lab where we'll be using the timer. Actually, Monday, what I will be talking about is the timers in more detail. We'll go through the timers and then how to use the timer interrupt in order to generate a square wave / and maybe we'll probably do 2 parts. We'll do one, which is basically a demo. I'll bring the scope in and we can just probe there and see that we can generate the square wave as we would like to see. And the other is we would just modify Blinky to using the timer instead of, because as you recall, last time when we did Blinky, we used that time delay routine where we did the nested loops. That just, when it's doing nested loops, what's the processor doing? Nothing. So if we wanted to generate a timer to blink a light on and off, we could have our processor do something completely different, and just every time that timer overflows, blink the light on and off. So it's a much more efficient use of our processor to do things like blinking lights or square waves and that, using timers versus using the interrupts and the timers versus using the delay loops. So that's there. So I'm going to wrap this up here. This is my shortest class. I hope